Okay, welcome to part 2 of this review for chapter 16 in carbohydrates. In the first part, we covered this first page. All right. Now we will complete this document and finish the second page. You should know the difference between a reducing and non-reducing sugar. I know I already talked about this earlier, but a reducing sugar, this gives you a positive, write it out, positive Fehling's or Benedict's test. The reason for that is a reducing sugar has a hemiacetal. Again, it's a cyclic hemiacetal. Oops. Okay. And this can open up to reveal the aldehyde so when this oxygen bonds to here, we get the hemiacetal. An aldehyde plus an alcohol gives us a hemiacetal. So we have the hemiacetal. This reaction is reversible, and it's the aldehyde that actually reacts with the copper in Fehling's or Benedict's test to give us a positive test in the process. This aldehyde gets oxidized to the acid. Copper gets reduced from copper 2 down to copper 1. Copper plus 2 down to copper plus 1. We see that color change. Non-reducing sugars, they don't have a hemiacetal, they have an acetal. So reducing, non-reducing sugar. Non-reducing sugar here has an acetal. And remember, when we first started talking about those guys, we said, well, they're stable, so it will not open up as a hemiacetal does, which means it does not reveal this aldehyde, which means it does not react with the copper in the Fehling's test, so it stays that blue color, it doesn't react. Ketohexose. Keto means ketone. Well, actually, the ketohexose we talked about was fructose. Right. So ketose means it's a ketone. Hexose means it's 6 carbons, so I'll put C6. So fructose, 1, 2, got the double of oxygen there, so CH2, OH, 3, 4, 1, 2, 3, 4, 5, 6. So we've got OHs on our alcohol groups on all these guys, but the key thing to remember here is with fructose, that carbonyl, carbon double bond oxygen, is not an aldehyde but a ketone, so it's on the second carbon. Aldohexoses we talked about too. There was glucose and galactose. Okay. Again, aldehyde for aldose and hexose, 6 carbons. Identify the common names, dietary sources, composition, and properties of the following carbohydrates. These monosaccharides don't really have a composition because they are monomers. But the dietary source, now the main dietary, the glucose is found in a number of things, but the main dietary source for glucose is going to be cereals and grains. The main dietary source, the only dietary source for galactose is dairy products. For fructose, it is fruit sugar, so fruits, and also sugar cane, sugar beets, and honey all contain fructose. The disaccharides, lactose, is composed of galactose and glucose, and of course it is from dairy products. Maltose is only glucose linked to glucose, And so it comes from starch, which is our grains and cereals. So remember, glucose comes from grains and cereals. Now glucose is found in not only lactose but also sucrose. Sucrose is composed of glucose, put a plus here, glucose and fructose. Okay, but in terms of the number of calories that most people eat, glucose is found here. Do it this way. Glucose is found in starch. Yeah, if you drink milk or eat cheese or whatnot, you're going to get some glucose from that, but it's not as much as you normally get from grains and cereals, starchy foods. Sucrose similarly contains glucose. This comes from fruits. I'm just going to fruits, sugar cane, sugar beets, and honey. That's where the fructose comes from, so sucrose also comes from there. Some common names here. Sucrose is table sugar. Lactose is milk sugar. Glucose is also known as blood sugar, and also known as dextrose. It's dextrose because it's dextrorotatory. It is the plus enantiomer. It rotates light, plane polarized light, in a clockwise fashion. Polysaccharides. Starch. First off, these are all contain only glucose. It's just a matter of how they're linked. Starch comes from plants. We have two flavors of starch, amylose and amylopectin. Amylose is straight chain, whereas amylopectin is branched. Glycogen comes from animals. So animals, also known as animal starch. It is a storage form of glucose. And then cellulose. Cellulose also comes from plants, but here it forms a structural role. Right, so it's plant fiber, and we can eat this, of course, and it's important for our diet as dietary fiber. Yes, here, describe and differentiate the components of plant starch, amylose, amylopectin. Right, so before we said both plants, they can only contains glucose. Now, starch, right, only contains glucose, but amylose, maybe I should use blue for this. Amylose, right, it only contains glucose, so I'm just going to say glucose linked alpha 1,4. It is not branched, so it's a very long helical molecule. What is a helix? It's a coil. Right? It's a long helical molecule containing thousands of these glucose monomers, and it turns in the presence of iodine. It turns the iodine turns blue. Amylopectin also contains only glucose, and they are likewise linked alpha 1,4, but also alpha 1,6 branches. So it kind of makes it a fuzzy molecule, so it has shorter helical sections because it's going to be coil, but we've got these branches kind of sticking out of it, such as that, and it turns purple in the presence of iodine. Okay, describes the components, properties, significance of glycogen, animal starch. Again, it's very similar to amylopectin okay, but it's more highly branched. So whereas amylopectin might be branched every 24 glucose units, glycogen is going to be branched about twice as much, so maybe every 12, 15 glucose monomers. So very similar to amylopectin, but more highly branched. This makes it highly mobilizable. I detailed what I meant by that in lecture. All right, so I detailed that in lecture. All I'm going to say is because it's more highly branched, it can be hydrolyzed and release glucose into the bloodstream faster. Makes it highly mobilizable. What does that mean? It can be hydrolyzed to release glucose into the blood faster, which is necessary if you're an animal that has to respond to their environment quickly. Plants do not have that necessity, so they can take their time. All right. Describe cellulose and differentiate from starch and glycogen. Cellulose, again, is not branched. So you have long helical fibers, right? But they are linked not alpha 1,4, but beta 1,4. So the anomeric carbon and carbon 1 of glucose is beta, so it's, beta is up. So it's up, and that's an acetal bond to carbon 4 of the next glucose unit in the chain. So it's linked. Beta 1,4 is not metabolized, so not used for fuel for the cell, but we still eat it, so in a sense it's still food, but used as dietary fiber. Okay. Describe the interaction between iodine and starch. Okay, so iodine, the diatomic molecule, right, I2, we can react that with starch. So we got this helical section. Right? And when you do that, the iodine actually bonds to this helix and it turns blue or purple depending upon the length of, I'll put a couple ones in here, depending upon the length of these helical sections. So a positive starch test or positive iodine test is when it goes from red to blue or purple. One other thing I should say about these polysaccharides, starch and iodine, go out like this. Each circle here is a glucose unit. So imagine this is thousands of glucose units long. Okay, there is a reducing end and a non-reducing end. The reducing end contains the hemiacetal. So right, contains the hemiacetal. The non-reducing end this just has alcohol groups sticking off of it, and these bonds here, these glycosidic bonds, are acetal bonds, so they are stable, they don't spontaneously open, but the hemiacetal here can, and it's this hemiacetal that reacts with the Fehling's reagent. Now, the reason starch, amylose, amylopectin, cellulose, and glycogen, these polysaccharides, do not give a positive failings test is because you only have one hemiacetal for maybe 1,000 glucose units. So it is really not enough of these hemiacetal bonds to give you a positive failings test. Yeah, it does give you obviously if it's helical, it's going to give you a positive iodine test, but a negative, so these polysaccharides give a negative failings test, or Benedict's test, because there is only one reducing end per thousands, could be tens of thousands of glucose units. Normal glucose, well, it's got one hemiacetal for every glucose. So this is orders of magnitude, if you wish, less concentrated in terms of the hemiacetal. So you get a negative failings test. Alright, so that should do it for this chapter on carbohydrates. Let me know if this was useful and if there's anything you'd like to see me do to improve it.